In differential geometry, the geodesic is a generalization of the notion of a straight line to curved spaces. The term geodesic comes from geodesy, the science of measuring the size and shape of Earth. In the original sense, a geodesic was the shortest route between 2 points on the Earth's surface, namely, a segment of a great circle. The term has been generalized to include measurements in much more general mathematical spaces. For example, in graph theory, one might consider a geodesic between two vertices, nodes of a graph. In the presence of an affine connection, a geodesic is defined to be a curve whose tangent vectors remain parallel if they are transported along it. If this connection is the Levi-Civita connection induced by a Riemannian metric, then the geodesics of the shortest path between points in the space. Geodesics are of particular importance in general relativity. Time-like geodesics in general relativity describe the motion of free-falling test particles. Introduction. The shortest path between 2 points in a curved space can be found by writing the equation for the length of a curve, and then minimizing this length using the calculus of variations. This has some minor technical problems because there is an infinite dimensional space of different ways to parameterize the shortest path. It is simpler to demand not only that the curve locally minimizes length but also that it is parameterized with constant velocity, meaning that the distance from f to f along the geodesic is proportional to s minus d. Equivalently, a different quantity may be defined, termed the energy of the curve. Minimizing the energy leads to the same equations for a geodesic. Intuitively, one can understand this second formulation by noting that an elastic band stretched between 2 points will contract its length, and in so doing will minimize its energy. The resulting shape of the band is a geodesic. In Riemannian geometry, geodesics are not the same as shortest curves between 2 points, though the two concepts are closely related. The difference is that geodesics are only locally the shortest distance between points, and are parameterized with constant velocity. Going the long way round on a great circle between 2 points on a sphere is a geodesic but not the shortest path between the points. The map T2 from the unit interval 2 itself gives the shortest path between 0 and 1, but is not a geodesic because the velocity of the corresponding motion of a point is not constant. Geodesics are commonly seen in the study of Riemannian geometry and more generally metric geometry. In general relativity, geodesics describe the motion of point particles under the influence of gravity alone. In particular, the path taken by a falling rock, an orbiting satellite, or the shape of a planetary orbit are all geodesics in curved spacetime. More generally, the topic of sub-Riemannian geometry deals with the paths that objects may take when they are not free, and the movement is constrained in various ways. This article presents the mathematical formalism involved in defining, finding, and proving the existence of geodesics, in the case of Riemannian and pseudo-Riemannian manifolds. The article Geodesic discusses the special case of general relativity in greater detail. Examples. The most familiar examples are the straight lines in Euclidean geometry. On a sphere, the images of geodesics of the great circles. The shortest path from point A to point B on a sphere is given by the shorter arc of the great circle passing through A and B. If A and B are antipodal points, then there are infinitely many shortest paths between them. Geodesics on an ellipsoid behave in a more complicated way than on a sphere. In particular, they are not closed in general. Computational methods. Efficient solvers for the minimal geodesic problem on surfaces posed as agonal equations can be found in applications. Geodesics serve as the basis to calculate geodesic airframes. See geodesic airframe or geodetic airframe. Geodesic structures, for example geodesic domes. Horizontal distances on a near-Earth. See Earth geodesics. Mapping images on surfaces for rendering. See UV mapping. Robot motion planning. See shortest path problem.